So I'm going to talk about what happened here? Okay. So I'm going to talk briefly about the motivation and the background, why we need SuperLite, and give a brief introduction because it's just half an hour talk. So a brief introduction to the methods using SuperNew and SuperLite and what are the differences, why SuperNew is different and SuperLite is necessary. Then I'll show some preliminary results with the model spectra that we produce using SuperLite. And I'll talk about the future work and development that is in process. So Manos had given a talk yesterday and most of you were present. So I'll not go into the details of superluminous supernovae, but the main reason that we are interested in these supernovae is that the supernovae are brighter, much brighter than the classical core collapse supernovae. And their extreme luminosities, they extend over 10 days and they are accompanied by a copious amount of UV flux. So this tells us that the superluminous supernovae originate from a progenitor, which are massive stars, and there is interaction with circumstellar medium. So there are broadly two types of superluminous supernovae. The type 1 are typical type 1c like supernovae where you have absence of helium and hydrogen lines, but you have strong silicon sulfur lines, just like type 1c. And type 2n like supernovae, which is superluminous supernovae of type 2, show a prominent emission line of hydrogen. So they show narrow emission lines. And we are more interested in the supernovae of type 2. So these type 2 supernovae, the narrow emission line that you see in the spectra, it indicates that there is a strong circumstellar material supernova ejecta interaction, which I'm going to abbreviate as CSI from here on. So we are interested in learning the effects of this interaction on the observed spectra. And we want to know what is the dominant mechanism that powers the superluminous supernovae. So what are the types, what are the spectral types of supernovae, and how they can be explained from the circumstellar interactions. So we want to study the sources of observed diversity, including type 1 supernovae, so superluminous supernovae. So we want to know whether we can have a unified model of superluminous supernovae where we can, based on the viewing angle and the different densities or different profiles of circumstellar material, can we explain the observed variations in the spectra of superluminous supernovae. So in general, we want to know whether superluminous supernovae, like Manos explained yesterday, superluminous supernovae are defined based on certain limit, but actually there is a continuity of observed maximum of light curve. So we want to know whether we want to study whether the classical core collapse supernovae and superluminous supernovae are in fact continuous range of progenitor interactions with circumstellar material. So before I start talking about SuperLite, let me introduce SuperNew in brief. So SuperNew is a Monte Carlo radiation transport code, and it's a multidimensional transport code which uses implicit Monte Carlo and discrete diffusion Monte Carlo methods. I'm not going into details of these methods since we have only half an hour for my talk, but if you're interested, we can talk about it later. So in Monte Carlo approach, we do not explicitly solve the equations of radiation transport. So what we do instead is we define a bundle of photon as the Monte Carlo particle, and we track the transport of this Monte Carlo particle using random number sampling to simulate the radiation transport. So based on the local temperature distribution, we find the probabilities of how these particles will propagate through the material. So each of these particles' history are independent of each other. So we can use parallel processing. So SuperNew is a MPI and OpenMP code. So you can use both a message passing interface and OpenMP methods so that you can speed up the calculations. And SuperNew has been successfully tested so far for classical kilonovae and type 1 supernovae, as well as type 2p supernovae. So everything which includes homologous expansion. So what is homologous expansion? So after the initial shock breakout phase, which is a hydrodynamic phase, in typical type 1a supernovae, the ejecta expands as function of time. So that this expansion is called homologous expansion, where the velocity grade is unchanging and the ejecta moves through this velocity grade. So velocity acts as a Lagrangian coordinate in SuperNew. And the density and velocity and the velocity gradient, everything is proportional to time. So it simplifies the equations of radiation transports because you can substitute all the quantities which include velocity gradients and density and velocity can be replaced by time. So you just need to know how much time has passed since you started the simulation and you get your profiles. But SuperNew, since it assumes homologous expansion and it does not include non-thermal radiative contributions, it's not sufficient to produce the spectra of type 2n or superluminous supernovae. In the LT assumption, the radiation temperature and gas temperature are in equilibrium, which as I shortly will show here, is not the case for type 2n supernovae. So in case of type 2n supernovae, where there's a circumstellar material interaction happening, the forward and reverse shock develop at the circumstellar interaction front. So there are strong velocity gradients that are developed. So the velocity is no longer homologous. It drops as at the interaction front, as well as there is a density peak which appears because of the forward and reverse shock. So here it shows type 2n profile from another code called Stella, which does radiation hydrodynamic evolution of the supernova ejecta. And as you see here, at 0.1 day, so just after the shock breakout, the photosphere is well in front of the shock. But as the time progresses, the ejecta expands and the photosphere also recedes because of the recombination. So how did that happen? So so when the photosphere reaches the shock breakout front, all the assumptions of LT and homologous expansion break. So we have to take into account the other effects, which are the Doppler effect. So in SuperNew, the Doppler effect is only the redshift of photons because the ejecta is only expanding outward. But in our case, we have to consider both the redshift and blue shift in the line forming region. We have to also consider the radiative cooling of lines. So just LT is not sufficient to produce the spectra or to correctly produce the spectra. And we also have to consider other non-trivial effects that Manos has discussed in his talk yesterday, the anisotropic electron scattering, line muting due to external illumination, etc. So this is the motivation behind SuperLite. So we want to have a code which includes all these effects taken into account and the non-homologous expansion. So what SuperLite does is it is not a radiation hydrodynamic evolution code. So it does not evolve the ejecta. But instead what it does is it takes the profile from another code like Stella, for example, which has already done the radiative hydrodynamic evolution of the ejecta. So at any given time, it takes the profile from Stella and it produces a snapshot spectrum. So ejecta is not evolved, it's a steady state solution. And the spectrum is generated based on the local properties which are there in the profile from Stella. So based on the radiation temperature of this profile, the packets, the MC particles are generated, and the transport of these particles is tracked through steady state and through the ejecta. So taking into account of all the non-homologous conditions and the true velocity gradient, so not the homologous expansion where velocity gradient is just proportional to 1/t, but the true velocity gradient, the particles are transported. So SuperLite, in SuperLite, all these equations are corrected. So all the assumptions are removed and the original forms of equations are implemented. In addition, currently the nebular approximation is implemented in SuperLite on top of LTE. So nebular approximation is an approximation which takes into account the line cooling effects, etc. This is a scheme that is described in Mazzali and Lucy 93, where we have the phi ij from LTE, where phi ij is the ionization population ratios that we have determined using LTE EOS, equation of state. And these populations are corrected for the dilution of radiation fields and all the line cooling and all other effects using this equation, where, again, I'm not going into detail of everything, but where W is the dilution factor, which takes into account of the radiation field geometric effects on radiation field, because radiation field is not isotropic anymore. And it also takes into account the radiation field correction and the recombination effects that take place in these regions. So the nebular approximation is a step towards non-LTE, but it's also not the complete non-LTE. So after giving the brief introduction, let me talk about the results that we got using SuperLite. So since SuperLite uses all these corrected equations, it also has to work in the limits of homologous expansion and LTE. So first we tested our code against the typical type 1a supernova. So the blue curve here is the spectrum which is predicted by SuperNew, the original code, using the evolution of the ejecta, so homologous expansion. So it starts at about 2 days after explosion, and it evolves the spectrum, evolves the ejecta through time. And this is the spectrum which is produced by SuperNew, the blue line, at 10 days. So I added features in SuperNew to save the profile at every few days. So at 10 days, we save a profile from SuperNew. So SuperNew has done evolution of spectrum. So we save the quantities like the velocity, the radii, densities, temperatures, etc. And we feed that information in SuperLite. And what you can see here is SuperLite does a good job in reproducing the spectrum that SuperNew predicts. So the green and the orange lines are both results from SuperLite. So it's a snapshot spectrum based on the profile that SuperNew generated. And in the orange one, it uses only the average temperature. So it assumes that the radiation temperature and gas temperature are equal, like in LTE. And the green curves is using the sampling of the MC particles using the radiation temperature. So the Monte Carlo particles are generated based on the radiation field. So the correct way to do it is using the radiation temperature. So what we find is that at least in this limit of homologous expansion and type 1a supernovae, SuperLite does a good job. Then the next step is type 2p supernovae. So again, type 2p does not have any interactions, but it's also not as simple as type 1a supernovae. However, there is a paper by Sanjana Curtis et al. That uses SuperNew to does the homologous evolution of type 2p spectra. So the blue curve again shows the supernu from their paper, supernu spectra from their paper, and the orange and the green show LT and nebular approximation spectra that is produced by SuperLite. And actually, SuperLite does a better job at producing the P Cygni profile that Manos talked about yesterday. So in a way, the spectra, type 2p spectra produced by SuperLite is a little bit better than SuperNu, because again, we have corrected all the approximations that are there in SuperNu. So now moving onward to the spectra of interest for our study. So that's the type 2n spectra. So A4 is one of the models that Manos discussed yesterday for his cold results. So this A4 is a type 2n progenitor, where the original progenitor has a 19 solar mass with circumstellar material of about 0.2 solar masses. So this plot, which I had shown earlier, is shows that as the photosphere recedes into the ejecta, as the time progresses, the photosphere gets closer to the CSI region. And as seen here, the LT assumption clearly breaks, because the average temperature of the shocked material is having a peak where the radiation temperature doesn't. So all these effects are very important for type 2n supernovae. So here is a test that we conducted for type 2n supernovae, where the spectrum from SuperLite at various stages of evolution is produced using SuperLite. So again, the stellar profile for this progenitor, so ejecta evolution, hydrodynamic evolution, were taken at different time, and these profiles were processed using SuperLite. And as you can see that we get the prominent H alpha line in our spectrum. And as the at about 20 days, when it's the closest to the interaction region, you get the strongest H alpha line. So just a sidetrack about the resolution. So as SuperLite is a post-processing code, we wanted to see how the truncation effects affect the spectra which is produced by SuperLite. So if we truncate the profile, the ejecta profile at different optical depths at different taus, then we see that as you include more and more ejecta, the prediction gets better, but also it gets brighter at the lower wavelengths, because you have more and more deeper regions which contribute to lower wavelengths. And at certain point, it starts converging. So why is this important? Is because, as we know, these computational simulations are very intense, and on a typical desktop type 2n spectrum, the post-processing takes about half an hour to 1 hour. So for tau equal to 100. So if you have more and more ejecta included, it's going to take longer and longer. So it's important to know how much ejecta we need to include so that we can do the computations faster. And the top plot shows the number of particles, packets that are generated. So as we can see, the number of packets, of course, the statistical noise decreases as you include more and more packets, but it does not significantly change the spectrum. So that is also a good test to see that the spectrum produced is not very sensitive to how many packets are initialized. The final thing I would like to talk about is the nebular approximation, which is implemented. Again, as shown earlier, the temperature profile for the circumstellar interaction is has a peak at the circumstellar interaction regions, and based on where we define our photosphere, we get different predictions for nebular approximation. So mostly when we set our photosphere at tau equal to 1, we get a better prediction for nebular approximation. And the lines which are produced by nebular approximation are slightly stronger than the LTE predictions of this spectra. So moving on to the work which is in progress. So now that we have a code which is producing the spectra, we have a suite of 50 models which are run using Stella code. So we would like to run different scenarios through SuperLite and produce spectra for these models. We also want to work on a 2D model. So since SuperNew is a 2D code and SuperLite also has 2D capabilities and 3D capabilities, we would like to explore how a 2D model with a disk of circumstellar material and produces spectra at different viewing angles and how that compares with the observed spectra. And in general, we want to study and compare the models of H-rich and H-poor circumstellar interactions and compare them with the observed spectra. So that is the science part. And in developmental part, we are working towards including a full coupling of radiation hydrodynamics. So what SuperNew does, but with all the assumptions removed. So we would have a code which actually evolves a spectra with hydrodynamics. And as for SuperLite, we would like to implement the shock illumination and it's not written here, but non-LT effects are also being implemented right now. So it's in the testing phase, but once it's also included, it will have all the capabilities that we want from SuperLite. So in summary, to best of our knowledge, SuperLite is the only Monte Carlo radiation transport code which is designed to post-process non-homologous interacting supernova ejecta and with non-LT effects included. And once fully equipped with non-LT and electron scattering effects, we will have a wide variety of applications that we can study with this code. And most importantly, SuperLite will be publicly available for the community to use. So that's all from me. Thank you.
Thank you very much, Guru. Other questions?
That's super exciting what you can do. I think a question that the first thing that comes to my mind is it's super interesting to study superluminous supernovae, but why is your focus there when there's like a lot of interacting supernovae that are happening in closer environments, and we have like a lot better observations for them because they are closer.
Right. So superluminous supernovae are interesting because they produce brighter or a magnitude brighter light clouds. So of course, as an object of interest, they are interesting. And in addition, since they are so bright, we can use them maybe as a cosmic beacon, like we use type 1 supernovae in future, where we can observe the distance, the superluminous events in distant galaxies, where we cannot observe the regular classical supernovae. And as I said, even if we are more focused on superluminous supernovae, we would also want to have a broader picture where if we can explain all kinds of supernovae with a continuous range of progenitor masses and circumstellar material around the progenitors, then of course that's the very long-term goal.
And you showed a lot of your model spectra. How do they actually compare to observed supernovae?
Okay. Well, in the test here, I'm not compared with any observed spectrum so far, but the super new comparisons, those were compared to observed spectra. So if super new and SuperLite are producing spectra which are comparable, then that's comparable to observations as well. But for type 2s, we have not yet done the comparison with observations.
There were also some differences. So Can you go to the type 2P spectrum?
Type 2P.
The
Yeah.
Right. So here I see some clear difference. First of all, the emission lines at 7,000 hertz due to this line.
No, it's actually a smoothing effect, but also super new does not include the non-homologous effect. So it's possible that it's producing lines which are not really there at that time.
It's not quite apples to apples because their model assumes LTE, assumes
Homology.
and all that stuff, and with SuperLite.
Yeah, sure. I was just wondering.
They're also doing a smoothing that we don't know exactly how many times over they smooth the spectrum. We don't do any smoothing. Well, you try to smooth out the Monte Carlo noise, so you have some Monte Carlo noise around the features, and you try to just highlight the main features, the real features in the spectrum. And so people often clean them up with
So you do boxcar smoothing or something like
box star.
on the spectrum.
They clean the noise basically.
Yeah.
I'm not sure I understand this.
But as far as the features go, I would trust more the SuperLite results than SuperNew because SuperNew does not have.
Actually, we had a comparison with an observation for
Recommend the test is to go to. Other questions?
It's just something about it. You do not smooth the result.
So yeah, so the thing is that because it's a post-processing, it does not. So in SuperNew, since it's evolutionary models, it
noise propagates.
the noise propagates, and also the packets which are initialized, some of them escape and some of like, so not all packets remain throughout the evolution. So the number of packets are also, you cannot use a lot of packets because then it's going to take a lot more time. But in post processing, you can actually use more packets. So in the SuperNew model, they had only like 2 to the 14 packets. So I had 2 to the 20. So the statistical noise drops as you have more.
The high number of yes.
Right. So if you use less packets, then you have more statistical noise, basically.
Okay.
So that's another advantage of doing post processing.
Yes, you don't need this.
Yeah. Okay. Sure. Yeah. Sure. No problem.
Do you think, or did you say there's some kind of like smoking going into say, you know, the spectrum of some interacting supernova really is formed by interaction or something else?
Maybe. I mean, that's the aim, is to see how the
Right, but you
observation.
compared, for example, you know, you have the models that you already did with CSM, and you have the ones which don't have it.
Right.
There's something obvious to look for.
Yeah, so when you have circumstantial interactions, you have obviously have a narrow emission line. Is that what you ask? I'm not getting
Yeah,
it.
right. Like for instance, if you say.
So when you have a type 2P where there is no interaction, you have a P-Sigma profile like this instead of a narrow emission line.
Yeah, but I'm guessing also that most of these observations are in the optical. So if you could, I don't know, predict like higher energy radiation, which maybe would be more obvious way to interaction.
You're not going to get X-ray spectra from this.
Yeah, I mean, this is not designed to.
30,000 angstroms.
And the limits, the lower limit. Is it arbitrary?
We don't include no.
Yeah, I mean, like the effects are not included. You have to take into account down scattering as well. So, yeah.
Okay, so let's thank you again and move on to the second speaker. So I will introduce him while setting up. So second speaker is Sagir Shiver, and he's also postdoc at LSU, and he started his career at Technion, Israel And then we move to whether it's you in 2019. First, we worked with geostation, and now he works with Manus, and he's going to talk about merger.
It's downloading.
Yeah.
It's a big fight.
Mhm.
4 minutes left.
4 minutes.
Yeah. Movies.
There are movies in
And continue the discussion a bit, I guess, until it downloads. Another thing that I wanted to ask, and I was going to ask offline, but since we have some extra time, is I didn't quite get how the type 1A spectra were produced with super. So can you elaborate with that? So did you use Stella to do the hydro and
No,
then?
no. So for super light, you're asking me, right? So for type 1A, Supernovae is designed to evolve type 1A.
Right, so it
Ejecta.
also does the hydro.
No, it
There's no
doesn't.
hydro.
It's homologous expansion.
Because it's a homologous expansion, there is no interactions.
I
So
see.
the
But those two things fixed.
Mhm.
and
But
the material just cruises through. The material which is farther from the center moves faster than the material which is closer to the center.
and there's no nucleosynthesis.
So the densities and everything does not change over time.
That's already been done in the explosion profile that we get. So W7 is a nominal type 1 explosion.
Right, so
model.
that okay.
So it does
Okay.
not need hydrodynamic evolution. So Supernovae does the radiation transport when with the expanding ejector. And I have added a feature in Supernovae to save the profile at each few days. The user can say how many days. So every few days, the profile will be saved. So I have saved the profile from Supernovae when it's running the
Okay, I see.
code, and then I use that profile in SuperLite. So it has the radiation, radius, velocity, temperature, radiation temperature, average temperature, all the valences,
I see. Okay,
density, etc. The mass.
I see. So when you'll be able to do the 3D profiles, will you also? Are there any plans to also do polarization?
You mean for spectrum predictions?
Yeah.
Yes, that's a goal. It's to be able to post-process the 3D interaction profiles, with which we can do super new right now under the assumption of homology. The goal is to be able to do that with SuperLite. So SuperLite already has built-in assumptions in that you can expand it to 2D and 3D geometry, and you can use you can post-process a flash simulation, for example, to get predictions.
So that currently all the physics is implemented. So only the geometric effects are trying to be included for 2D and 3D.
Pretty trivial. So to add those things.
Once we have major implementations of NLT and electron gas scattering, then going to 2D may not, need not take a lot of time,
Okay, interesting.
which is a trivial geometric corrections.
Thanks.
It's downloaded.
1 minute. 1 minute and 20 seconds.
Okay, maybe other questions?
Could be another question. You're using your code to process some results of information codes. And And so you have these stationary states, and then you do the rest to break the spectra. So for the spectra to be fair, meaning that all the phenomena happening in the source will happen with a time scale that's much larger than
Right. Right. So in this,
in the states or in this.
yeah, so it's an approximation that is infinite time. So there's a fudge factor to set the time. So by default, the time is set to the time, C over R. So speed of light divided by the length of the profile. So it's like enough time for everything to propagate. But in addition, you can have a fudge factor, which I have not included the plots here, but even if I use like 2 or 3 times the dt, that's just going to change the spectrum. So correctly takes into account the steady state resolution. So in steady state, there is no evolution happening. So the profile doesn't change. Only the photons and transport would.
I'm asking questions because we don't use the photons that are trapped in these high inspirations and things like that. And so I think does this may change like in a very short time scale? I have no idea.
Right. That's why that skill set to be very large.
But that's the next development target, is to couple the hydrodynamics with Monte Carlo radiation transport.
So then you do actual evolution on the spectrum. So at every step, the profile, physical profile will be updated in hydrodynamic step, and then the radiation transport will be conducted. So that's like the evolution of the
Feedback loop between
so
the.
there'll be like yeah. That.
You see it on.
Not yet. Yes, I can see it now. Okay.
The size is good.
The size, I don't think I can affect. I can change it from here. So what did you do before?
So I actually used 4x3 in the presentation itself while making the slides.
Ah, okay. So yeah, I don't think I can change it from here. So why don't we just start and then?
Okay. So thank you for waiting. Release the view. I will show results from simulation arbitrary files the last couple of years with this happening code called Doppler Tiger. So Doppler Tiger is an atomic code, 3-dimensional, but which is getting its name from the LSU football team, the LSU Tigers. So if you walk in campus and the Louisiana State University, you see everywhere there is store, there is a tiger there. There is about football there, especially college football. In the first year, I was doing the postdoc there. They actually won the championship. So there was a big celebration. Anyhow, they developed the code of the tiger, a collaboration between the Center for Computation Technology and the physical department. Physics and astronomy department, and it's an open source code, so you are welcome to use it. Just go to the GitHub page, download, and you can start working, simulating. So why use OpenTiger? So first is the GUI-based code, which has an adaptive metric finder, so you can resolve different regions simulations at different resolutions. Also, there's excellent conservation properties that conserves mass and energy to a very precise degree. In one of the simulations, for example, we have observed mass to 1 power to 10 to minus 11, which is almost a machine position. And so the angular momentum is conserved very well. We can get to a conservation of less than 1% at 40 orbits. For example, in one of the simulations. So that's really designed to simulate binary where the angular momentum conservation is very important. The next thing that on top of that, Autotiger use HPX for its parallelization. So traditionally, the parallelization is using MPI plus open MPI to run clusters on large numbers of cores. But we are using HPX, which is also developed at LSU. HPX distributes the work between all the nodes independently behind the scenes, and it also enables us to scale to very large numbers of cores. It also enables us to use GPU if you want, or different architectures. So you can see that this the equation that Autotiger solves, basically the hydrodynamic equations and the gravity equation. It's important thing to note about Autotiger that we solve the equation, the dynamic equations on a rotating grid. So we have a parameter omega, which is constant, in which the grid rotates in an entire simulation. We set it usually to the initial binary frequency. We are doing that because in this way we reduce numerical viscosity of text. So once the grid is rotating with the binary, there is less viscosity and angular momentum is conserved better. It also can involve several species together, and of course we have equation sets to actually solve the equations. So all of this make Autotiger ideal for simulating binary interaction. We can use high resolution on short work times, and we can increase accuracy. Some of the systems that we simulated are listed here. Double white dwarf mergers, but we simulated the Chandra-Sakali mass, so we don't have the type 1s supernova. Instead, we have a merger of the carbon oxygen white dwarf and any white dwarf, and this will evolve later to be a unique type of star called Boreal star. We also simulated contact binaries, which then merge and produce a transient, which is very similar to the determinized score event that is very well observed and documented. So I will show you these two examples next. The common things that all these mergers have is that they have transients when they merge. Also, the single star, the merger product, has unique properties that cannot be achieved in a single star evolution. So you have to have binary for that and a vector. So white dwarf merger. They are one of the scenarios suggested for the formation of output stars. So you have carbon oxygen white dwarf with the helium white dwarf. The mass of the helium white dwarf is smaller than that of the carbon oxygen, and that's why it's a little bit larger. And the total mass is less than the standard Sakara limit, it's 0.9 solar mass, for example. Then there are some gravitational wave emissions, they start to produce, and at some point, the helium white dwarf start transferring mass to the carbon oxygen mass, carbon oxygen white dwarf. In some condition, like in mass ratio of 0.7, this mass transfer is unstable, and this will lead to the disruption of the helium white dwarf onto the carbon oxygen white dwarf. So we have a shell of burning because we get temperature, high temperature due to the disruption, and this shell, there is helium burning, but the helium burning is partial, it's not complete. And outside the shell, you have helium which is not burned. So this kind of structure later evolves, and you get giant star because the helium get expanded because of the burning of the shell, and you have a giant which is rich in carbon, but is very efficient in hydrogen. Okay, so and this will resemble the output stars, which also a unique character of this type of star is that the ratio of oxygen 16 to oxygen 18 is low. Because you do, in the nuclear reaction, you have a partial burning, so you produce the oxygen 18, but oxygen 18 is not then destroyed by another alpha process. That's why it's called partial. So you end up with a lot of oxygen 18 and oxygen 16 almost in the same abundance. So this is the setup of the simulations. We have some properties of the binary. This is mass ratio of 2.7. Now I will show you a movie of this simulation. So I show you equatorial plane. This is the temperature. On the left corner, you can see the time in initial orbits. And what you can see is that initially the white dwarfs are cold with zero temperature, but once mass transfer begins, the helium transfer mass to the carbon oxygen, and there is a heating die shocks. The stream is free falling on the carbon oxygen white dwarf, and it gets heated. Right now, the condition is not yet to helium burning, but when the measure itself will happen, the temperature will go over 10 to the 8th, and considerable burning can happen on onto the surface of the carbon oxygen white dwarf. So now, there's a lot of interesting stuff going on there. The instability of the orbit is very interesting to see. And we explore this merger and what it will produce. For example, we look at helium burning by the triple alpha process, and we can look in the simulation domain where we have a lot of burning. What is the power of a nuclear reaction in every cell? And then I can plot it, and I found that it's indeed in a shell around the carbon oxygen white dwarf. And this is on the left, you see the equatorial, on the meridional, and the right, you see the meridional. You can see that there is actually considerable burning happens on the poles. This can affect maybe the shape, but overall, the nuclear energy that is produced in this type of binary, this type of major, is negligible compared to the binding energy of the white dwarf. So it's not expected to affect the dynamical process. That's confirming our assumption that we only include hydrodynamic effects and not nuclear reactions. Now I will go to another type of simulation. This is a luminous red nova, or some transient that we thought that is caused by stellar merger. Some of them like V1309 or V838 monosophorus. So you can see the absolute magnitude and the duration of the event. So we want to simulate something like that. We have a merger of the V1309 score. I will show you another movie. Here it's a movie of density. So we start with a constant binary. We have the secondary start accreting mass from the primary, and there is also some outflow from the L2 point, some mass will leak out of the L2. Actually, we think that this merger is induced by Darwin instability other than just a mass transfer, and then we have a merger. And it's very interesting to look how this will how the life curve of this process will be, it will be like observation. We're still processing this data, and we wait until several orbits after the merger to have a spherical, not spherical, but azimuthal symmetry structure that we can then make more processing of this structure. But now I want to focus on the work I'm doing about a massive star. So the motivation is that well, exist several observations of supergiants and giants that rapidly rotating. For example, Betelgeuse, it's a very known star. It's some unique properties, but I will focus on the fact that it is a fast rotator. So the surface rotation is about 5 kilometers per second. And if you take simple angular momentum arguments and you want to see what will be the surface rotation, so you assume like in the main sequence phase, Betelgeuse as 100 kilometers per second, but then on the giant phase, it increases its radius by a factor of 50. You get that on this the giant phase, it will be the surface velocity will be 2 kilometers per second. And if you're doing the calculation more accurately, you will see that the actual velocity should be smaller. So the conclusion is a single star cannot evolve to have such fast rotation on the equatorial, and a binary must be involved. So that's what we're doing. We have a binary which has a massive star. So we have a binary of 16 plus 4 solar mass. We evolved each star in MESA separately. And then we imported the MESA profile to Octotiger, from 1D to 3D. So the primary is on the way to become a red supergiant. So we don't have helium burn, hydrogen burning at the core, only on the shell. And the radius is as written. The secondary is the main sequence star, is 20 times smaller than the primary. And this can have some difficulty in simulating this because of numerical challenges. It's because of this big difference. But we have an AMR grid, so we can use it to resolve the secondary even more. The initial separation is such that the primary just feed its threshold, so we can initiate mass transfer from the beginning. So here I present a movie of pressure in that tutorial. You can see the secondary, and you can see also the grid and of the simulation. It's starting spiraling into the primary, and what it's important to notice is that this interaction. This simulation is still ongoing, and it's slowly entering into the primary. You can see also density contours, and eventually we want this system to merge. Right now it's around orbit 22, and we see that it's almost there, but it's not there. So that's where it's the last snapshot of the simulation. So it's very close to be inside the envelope. I mean, there is also right now a common envelope, but we wait to enter more, and then we put some spiral in, or maybe plunging, and the secondary should merge with the core of the primary. That's the goal of this simulation. And we will see. We hope it will happen in the next few days. Then we call it a Greek merger. That's some challenges, as I mentioned, stability issues. So you take 1D in MESA and you import it to 3D. You have a different resolutions, different in equation states, and when you compare the initial or the states of the pressure profile to the MESA, you get that the star suddenly collapse. So you cannot simulate this that longer. So the solution for that, we run several resolution, and we also added equation states more resemble the MESA one. We added a radiation pressure to the ideal gas, which we usually use. Then we found it's more stable, but overall there is a need for a manual resolution to keep the primary stable, and that's what we did in the simulation that I showed earlier. While it's running, we are working on how to import better the method profile, and one of the methods that I implemented recently, that's a direct mapping, just a cubic interpolation of the MESA profile, density, and pressure, and you can see that in this case, they really match the MESA profile. There will be issues of stability that later on, and for that, we think that in order to see that there is a very dense form, so we might need to add point particles to our tiger in order to really simulate massive stars as much as we want. I want to put on a different subject, but on the same matter. So we saw a simulation where the companion is accreting mass, and that's leads me to what I did in my PhD, where we assume that if a companion main sequence star accretes mass at the high rate, it will launch jets that are perpendicular to the orbital plane. And then the jets can add in the removal of the giant envelope. They can even postpone or prevent common envelope. And then we will have a grazing envelope, a term that was named by my advisor at the time, also Carlo. So you have a binary, you have a companion at the surface of the primary. It runs jets, so the orbital separation and the radius of the primary shrink simultaneously. So it seems like the companion is always raising the envelope while it's firing. Another effect of the jets that they will have some, they will affect the outflow, and they will have some asymmetry in the outflow. So I investigate this possibility. I tried several different companion mass. The primary was kept the same. We have a primary of 0.9 solar mass and the envelope of 0.5 solar mass and different companions. And I found that for the lowermost companion, the jets are the most efficient. You can see that for the 0.1 companion, we unbind with jets most of the envelope. And also the evolution is more of a grazing instead of a plunge into a common envelope. I will show a 3D movie of that. Oh, sorry, it was running. So the companion launch jets perpendicular to the orbital plane. There's some tidal introduction that lift the bulge from the primary and start trailing the companion. At some point, the bulge will engulf the companion, but you need to remember that the companion always launch jets. So the jets interact with the envelope and expel mass to all directions. And basically, the envelope is being raised by the jets while it's firing in. So you get a lot of mass which outflow to all directions, but in the polar direction, you have a faster outflow. This is what I present here. You have fastest is the from the equatorial average outer velocity. So with jets, you have higher velocity at the poles. So the conclusion was that in this mechanism, we can produce bipolar nebula, like planetary nebula, which are bipolar. And this was interesting, the results defined. Now I will summarize. Tiger, as I showed you, is ideal for simulating binary interaction of stellar mergers. We simulated a binary of carbon oxygen white dwarf and the helium white dwarf. Also simulated the big continuous force simulation, and we need to analyze the results. And also there is this simulation of massive binary, which is still ongoing and waiting to be merged. Our future plans. As I said, we want to implement point mass particle into our Tiger. And we want to include a better equation of states that takes recombination processes, which MESA, like the one in MESA. The next thing that we want to do is to take the post-merger object, like the massive merger, and to import it back to MESA for a long evolution, long nuclear evolution. And then we can do post-processing also with the new MPPN code. We can track the nucleosynthesis for a longer term, and with an extended chain of isotope more than 1,000. And so we have some ejecta in the simulation, some of it unbound. We want to check the kinematics of the properties and the energetic, and to find what will be the environment of such a merger. Because if the massive there's a merger, there's the massive star, the massive merger will then maybe explode in supernova, and there will be interaction with this environment. What else we can do is we are planning to take the merge burst and to calculate the light curve from that using Supernovae or using SuperLite. Yeah. Overall, the big picture, what we want to do is to be able to simulate a merger on the different relevant timescales, from nuclear timescales where we can evolve it in MESA, then we can simulate the merger in dynamical times in 3D, and also we can take the 3D back to 1D or to some autonomic radiation transport code and even look on the light curve. Yeah, and with that note, I will finish.
Just something small I wanted to ask about the white dwarf merger that you were talking about. So just wanted to make sure that I understood this reaction that you were talking about that changes the ratio of isotopes of oxygen.
Yes.
Is that the thing that would make like a merger of two white dwarfs different from like a single star with a core of two solar masses that then gets merged?
Right.
Yeah.
So you need a partial burning. So you need not only that this will that one reaction will do, but that the other one will not proceed.
Yeah.
So that's the difficulty. So you say that there is another process that can do the same?
No, I'm asking like if you just have a normal star that has like two solar mass and you strip the envelope somehow, then that would be different from the merger of two white dwarfs.
Yeah, but
right?
so
Is it because like is this reaction one
so
of the
what you're saying is referring to another possibility of the formation of Alcott star, which is I call this like the single degenerate. But with the recent findings, they found out that this can almost be ruled out because of the oxygen 18 to oxygen 16 ratio. You can get hydrogen deficient, but you will not get this partial burning. That's the coincidence.
Also, we just found in the recent work on the Arc-Bohr simulations that you will have another, not S, not R process nucleosynthesis, but I cross nuclear synthesis, which has been largely overlooked in the context of mergers.
So I wanted to ask about the Betelgeuse simulation. Is there any particular reason you chose this combination of both masses or initial parameters?
Yeah.
Or what was
Yeah.
the motivation?
So in earlier study, Manos was work on that, and they had several suggestions for this binary, and they found that that would be ideal for reducing the rotation, right?
Rotation and the nitrogen to carbon surface abundance, which is enriched because of the extra mixing that you have in your application. So we did a variety of models, and that was the best fit.
Both codes have great potential. Congratulations.
Thanks. Thank you.
All right, if there are no further questions, let us thank all our speakers again. Thank you.